Hello, Royals. Let's take a look at lesson 5.5, applications of trig derivatives. And I want to have another example to stress the importance of radian mode. I believe example number 4 from the lesson, and example number 5 should have shown you that, but let's have a conversation about it with another example here. So I'm going to set up an example. Why don't you copy it down? You can try it on your own and then replay the video and see how you did. We have a man standing 3 meters from a vertical wall. I'm going to start with a sketch, of course. There we go. And he points a laser at the wall. And then we're told that he inclines the beam at a constant rate of 10 degrees per second. Doesn't say that he's moving left or right, so let's assume that that's constant. And we want to know how fast the point on the wall is rising when the beam's angle of elevation is 60 degrees. So I'm going to start off with a declaration of the given find when. I'm seeing this as like a related rates question. Looks like I am given d theta delta theta by delta t is positive 10 degrees per second. I want to find, I'll call this the height, delta h by delta t when theta is 60 degrees. So it looks like I should declare theta, h, and t. Let theta, h, and t represent the angle of elevation. H was the height of the point. It could be, say, on the wall. And time. In. And the question gives me the rate in degrees per second, and it gives me the angle in degrees. So I'm going to choose to let theta be in degrees. In degrees, h is in meters, I believe. Meters. And time is in seconds. Okay. And we'll see how this works, or how it doesn't work. Okay, I am going to, sorry, I'm on the edge here. I'm going to start by trying to relate my variables, and then I will relate their rates. I like this approach better than sort of building a chain. So relation between my variables, I'm seeing a tangent ratio here. Let's say that the tangent of theta is going to be h divided by 3. Let's go ahead and include the units again on this example. I think this might work out a little bit easier than the one in the lesson. So that 3 there is measured in meters. The height will be measured in meters as well, but that'll happen on its own. Tangent of theta is a unitless ratio. If I'm trying to find dh by dt, I might choose to isolate here. This is another example of how a little bit of simplification before differentiation will make things simpler. And now I am set to differentiate with respect to time to find my dh by dt. So I can differentiate with respect to time on both sides, and I'll just have a chain rule on the left-hand side. On the right-hand side. On the left-hand side, I'll have the rate of change of height with respect to time being, let's do constant multiple of 3. Again, I'm going to keep the meters for now. Derivative of the tangent of theta. Let's see, tangent of theta has a cosine of theta in the denominator. So does secant of theta. There has to be 2 factors. This was the secant of theta squared. And then my chain, d theta by dt. Okay. All right. The setup of this question is actually relatively straightforward because I'm given the angle, and I need to know the value of this ratio at that instant. Trickier questions might give you the time if you know where you were starting from, or the height, and then you would have to find the angle. But yeah, I'm set to substitute in here. I think I'm set to substitute in here. dh by dt then is going to be 3 meters. Let's say when theta is equal to 60 degrees. Is going to be 3 meters multiplied by, let's see, I'll do this as the reciprocal of the cosine of 60 degrees squared. multiplied by d theta by dt. I'm going to use the 10 degrees per second that I was given. Okay, so this means that dh by dt when theta is 60 degrees should be 3 meters multiplied by, let's see, the cosine of 60 degrees is 1/2. The square of that is 1/4. The reciprocal of that is 4, but that is a unitless ratio. And then I multiply this by 10 degrees per second. I'm not suggesting that you have to use your units all of the time, but here's the problem. There's a couple of problems here. One, we were taught degree mode before radian mode, and that is probably the only reason why we think that degree mode is easier. It is a struggle in advanced functions to convince some students that radian mode is actually easier to use. This is not a conversation about ease of use. This is a necessity now. Turns out that my let statements are incorrect. I decided I want theta to be measured in degrees, and I wanted d theta by dt to be measured in degrees per second. Well, I actually can't do that. That choice is wrong. If I multiply these numbers together, I get 3 times 4 times 10. That would give me, what, 120? But look at my units. If a student is used to maybe not substituting in units and they just trust that dH by dt is going to be in meters per second, then they would think that this rate of change is going to be 120 meters per second. But it's not. It's going to be 120 meters degrees per second. And what is a meter degree per second? I have absolutely no idea. So I took an incorrect approach. I actually was not allowed to have d theta by dt to be measured in degrees per second. Now, am I allowed to have theta measured in degrees? It turns out not to really matter. The cosine of 60 degrees is going to be the same as the cosine of pi by 3. Pi by 3 is 60 degrees, but it's my rate of change. It's my d theta by dt that has to be measured in per second. It has to be measured in radians per second, a unitless per second, for these units to correspond. If I want delta h by delta t to be measured in meters per second, then I cannot have a degrees per second in here. Okay? So let's fix this, I suppose. Let's see if we can just go back here or convert this. We're given d theta by dt is 10 degrees per second. I'll do a conversion up here. I like converting by multiplying by 1. I want to eliminate degrees and convert to a unitless radian. This is, I don't need to write radians there, but a lot of students feel more comfortable writing that there. And that gives me that d theta by dt is pi by 18 per second. I'll leave the 60 degrees in here, but I could also convert that to pi by 3 just to sort of illustrate. And then I suppose I want to change my let statement as well. Let theta, h, and t be in. So this is where if I'm mentioning units for all of my other quantities, you probably want to say, you don't want to say in nothing meters and seconds. Although I would accept that as well. Let's put in radians. We don't need to change any of this work here. None of this needs to be changed. Even this right here, this doesn't need to be changed because these two values are equivalent. The cosine of 60 degrees is equal to the cosine of pi by 3. It's this number right here that we have to change. That can't be in degrees per second. That has to be in per second. Let's scribble that out and write in pi by 18 per second. And that gives me 3 meters times a unitless 4 multiplied by pi by 18 per second. And that makes, or ensures, let's say, that my units for dH by dt will be in meters per second. And then as far as my answer goes, I suppose I'd have 12 pi by 18. What's that? 2 pi by 3 meters per second, which is kind of an awkward answer. Maybe we would be expected to round that off. 2 times pi divided by 3 to about 2.09 meters per second. So I think this is a really interesting conversation, and I wish it happened sooner in our math courses. We introduce radian mode after students are used to degree mode after years of using degree mode. And it's again, it's a struggle to convince students that it's useful. They don't like it. They don't think it makes sense. But reflect on that, because the only reason why degree mode makes sense to you is because someone told you one full rotation is 360 degrees. And if you look up the history of that, that's kind of based on a fallacy, isn't it? So we don't really even need to have a conversation now about what is better. What are some of the advantages of using radian mode here? Well, it works. It's required. Being required is a pretty big advantage in my book. And the choice of, well, what are some of the disadvantages of using degree mode here? Well, it's not going to work. That's a I'm not sure I need more disadvantages than that. Okay. Take a look through the other examples that we did in lessons, because sometimes we don't need the rate of change of the angle. We use degree mode in a number of other problems when we didn't need the rate of change of the angle. But if you want to be safe, you should always be able to work in radian mode. Okay, this is a very important fact. Keep your eyes open for this as we continue with trig derivatives.